All right, so sections 4.3 and 4.4, definite integration. So just a reminder, whenever we did this in the past, okay, so whenever we had integrals of f of x dx, we're supposed to write like big F of x plus c, okay? So that's what's supposed to happen when we have something like that, okay? What we're going to be working on today is, so that this is what we call an indefinite integral. And the reason why it's indefinite is because it has no upper and lower bounds. Okay, so a definite integral will look like this. Okay, and I'm not even giving you the main definition for this yet, but we'll talk about it later. This is actually the first fundamental theorem of calculus, but we'll define it. But this is called a definite integral. Okay, and it has upper and lower bounds. So just to highlight it here, right? It has an A and a B. So that means that you have something where this is defined. Okay, and we'll get to that definition that I wrote right there. It's actually called the FTOC, the Fundamental Theorem of Calculus. But I'll give you guys a definition of that in a bit. Okay, but the first thing they want you guys to know is Theorem 4.5. So let's put this right here. Theorem 4.5. And it basically says that continuity implies integrability. So continuity implies integrability. Now, there's a big old definition that they talk about with this, but it says if f, I'm going to kind of shorten it up a bit. If f is continuous on A to B, closed interval, on the closed interval from A to B, then f can be integrated on that closed interval A to B. So if a function is continuous, then you can integrate it. Continuous within that interval, you can integrate it within that same interval. So that's the first thing that they tell us. Now, the second thing that they tell us from Theorem 4.6 is that definite integrals are areas of regions. So definite integrals are areas of regions. And this is kind of important because you guys are going to have a problem based on this idea. Okay? So let me give you this definition. And the reason why I say this is because I'm going to kind of erase this soon. But you don't have to write this down. We'll talk about this later, but just kind of pay attention really quick. Okay, so don't write this down. But I'm going to give you a problem, something similar to this on your final exam. And I'm going to say, let's say this is 0 to 7. I'm going to say, what's the integral from 0 to 7 of this function? And let's say we know that's 4, and this is 3. And we'll say this is like 5. Okay? Again, don't write this down. Just kind of look at it. Because we'll do a better example of this later on. Okay? But if I were to tell you, like, what's the integral from 0 to 7 of f of x dx? And I don't even give you the function or anything for you to integrate, but I just gave you basically that picture right there. Well, this theorem up here says that definite integrals, that's what it is, right? 0 to 7 of f of x dx, are areas. So this is where you need your geometry. So you're going to say, oh, okay, let's see. This is at about 2.5. That's a semicircle. So the area of this would be 1/2 pi r squared, right? So you would plug in your information there. And then the area of this is 1/2 base times height. So you plug in your information there. You know this is 2 units and 3 units there, right? You know that this radius is 2.5 long. So all you have to do is calculate this and that and add it together. And that's your integral. Because integration is the same as finding area. Right? So if all you have to do is just find the area, add it up, and that's going to give you your integral value. Okay? And you're supposed to know this based on the following theorem that I'm about to give you, and because of Riemann sums, right? Riemann sums basically said, hey, if you can figure out the area to these things, then you can estimate an area, right? So all this stuff, again, don't worry about it. We will write it out a lot nicer in a bit, okay? But this is the idea of this theorem. It basically says, hey, if you can figure out the area of a function by any means, that means you basically integrate it. So let me give you that definition here. It says, if f is continuous and non-negative, on the integral from a to b, then the area of the region I'm going to highlight that. Then the area of the region bounded by f the x-axis and the vertical lines A and B x equals to A and x equals to B is, so area equal to the integral from A to B of f of x dx. So notice they actually said that an integral is equal to area. Okay, and we talked about that before, like this is what's given to us, that area is the same as taking an integral. So if you just calculate the area of stuff, you could say that you integrated it as well. So, you know what I just realized? I forgot to write f. I think I said it. The very first part of the sentence, if f is continuous and non-negative. I just put if. I think I said it, but I just read it right now and I'm like, I forgot to put the letter f. So if f is continuous and non-negative on A to B, then the area of the region bounded by f, the x-axis and the vertical lines x equal to A and x equal to B is... So let me show you a real quick example on this. Like I said, I was going to do one of these things. So, example number 1. Find the integral from 2 to 5 of f of x, or actually let me do this. I'm going to put x dx. So let me graph this for us. So we know, at least if I graph it this way, let me see. This is f of x equal to x. So according to definition, it says if I'm going to integrate from 2 to 5 of x dx, okay, the function x, then it's the same as if I actually drew the function. And I'm going to actually just put tick marks right here, just for the purpose of this problem. This will be 1, this will be 1. They say the integral is the area bounded by the function, the x-axis. So this is the function, right? The function, the x-axis, and then the vertical lines x equal to a and x equal to b. So let me draw that in red here. X equal to 2 and x equal to 5. So here's the area they're talking about. This is my integral. Okay? That's my integral. So they're saying if you're going to integrate, it's the same as finding that area. Well, what kind of shape is that? That's a trapezoid, right? What's the height of my trapezoid here? This is my height right here. What's the height of it? 3 units. What is one of the bases? Let's say this big one over here. How tall is it? 5 units. Yeah, 5 units. What about this smaller one? It's 2. So all you have to know to integrate from 2 to 5 x dx, it's the same as finding the area of that trapezoid. Okay, notice we're doing it this way because we don't know the fundamental theorem of calculus yet. We will know it soon. And then you're going to say, oh, that's a lot easier than remembering my geometry. But still, there's going to be a problem on your final where you're going to have to remember your geometry just like this. Okay, because I'm not going to give you a function. You're not going to be able to integrate. It's just going to be a bunch of little geometric shapes, and you're going to say, okay, the area of this and the area of this and the area of this is the following. Add it together. That's my answer. Okay, but in our case right here, I gave you an actual function. Now we know the height is 3. And one of the bases is 2, and the other base is 5. So it's 1/2 of 3 times 7. So this will be 21 over 2. And there you go. You just integrated. Even though we didn't actually do the integral, we just found the area. But that's the point. Integration is area. If you can find the area easier than you can do the integration process, then go ahead. There's nothing wrong with that. Because Theorem 4.6 said that integration is the same as finding area. So we just did this geometrically. Notice how the yellow area is bounded. Okay, it's restricted by the function, by the x-axis, by x equal to 2, and by x equal to 5. That's what that theorem above basically said, is that it's basically bounded by a and b, the function, and the x-axis. Any questions on this one? Are we okay? Just a little bit of geometry, right? So let's talk about some properties of this. So basic properties. Basic properties of integrals. Now these are important because every time you see these, you can get for one of these you can get a really quick answer, and for the other one, you know what you have to do if you have to switch things around. So, number 1, it says if f is defined at x equal to a, then the integral from a to a of f of x dx is equal to 0. If f is defined at x equal to a, then the integral from a to a of f of x dx is 0. Can anybody make any sense of that? Like, why is it 0? I mean, I'm imagining this in my head and it makes perfect sense. But then again, I know exactly what I'm picturing, right? Does anybody know what this looks like? The area of a function from a to a. Let's look at the top function up here. Okay? Whoops. Let's look at that top function. If I drew everything the same, but I said from x equal to 2 to x equal to 2, it's just a straight line, right? And does a straight line, vertical line, have any area? No. So that makes sense. If you're integrating from a to a, or from 2 to 2, or from 5 to 5, or 7 to 7, or -3 to -3, the area is a vertical line which has no area. Okay, there's no width to it. There might be a height, but there's no width. So when you're trying to find b times h or half b times h or whatever, one of those values is 0. It's going to 0 out. Okay, so when you integrate from a to a, then you get no area. Now there's a second one here. It says if f is integrable, is integrable. In other words, you can take an integral for it on a to b. Notice a is the small number, b is the big one, right? Because whenever we write intervals, we go from small to large. So a is the small number, b is big. Then the integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. In other words, they're saying if you wrote the integral backwards, if you said, I'm going to integrate from 5 to 2. So instead of going from left to right, you're going right to left when you integrate. If that's what the problem says, then you can fix it by flipping over the upper and lower bounds to make them look proper, right? The lower bound should be smaller, the upper bound should be bigger. But make sure you put a negative in front of the integral. So this is basically telling us you can have negative area. Okay? So how the heck do we have negative area? Well, it's like this. If you're at the beach, right? And you decide that you're going to dig a hole. All the sand that you took out is positive area. But the sand that is now missing, that's negative area. Because if you put the positive area in with the negative area, what should its sum be? 0, and it's supposed to flatten out again, right? So if I throw all this stuff back in here, then what I end up having is this again. This is why waves cancel out whenever you're in the ocean and stuff, because the ocean is moving in a sine wave fashion, or if you want to say cosine, doesn't really matter, but it's either one. And whenever you get a wave forming, and then like sometimes when you're at the beach, you notice like the wave looks like it's about to form, and it looks like it's gonna get big, and then by the time it gets to you, it's a dud, right? It didn't do anything. The reason is that there was a negative wave going at it, and when they met at some point, they canceled each other out, and then it just came in like just a little bit of motion of water, right? So this happens all the time in the ocean. Positive and negative areas colliding. Okay, how do they get those huge swells that you guys see in the movies, like those really big waves? It's because they get a couple of positive sine functions that happen to meet at their high points at one point, and those things just grow big, right? Because they just amplify each other over and over again. So, I mean, you get a lot of cancellations, but some of them become amplifications. So it's all based on I guess you could say it's all mathematical. But anyway, so yeah, if they're upside down, if the bigger numbers on the bottom, the smaller numbers on top, flip them over and make it negative. Okay, so just a real quick example for this. I'll let you guys. Actually, I can't let you guys do it yet. Let me give you the fundamental theorem of calculus first. So, theorem 4.9. Let me start again. Theorem 4.9 is what we call the FTOC, okay? The fundamental theorem of calculus. Again, FTOC. That's usually what you'll hear me say every once in a while. So the fundamental theorem of calculus basically says this. If you're going to integrate from a to b of f of x dx, then your answer is big F of x from a to b, which is the same as writing, or big F of b minus big F of a. So notice you take the upper bound and plug it in first, and then you subtract the lower bound plugged in. And right now we'll show you that, how that works. But yeah, there's a lot. This whole section is a lot of properties, and then tomorrow we'll try doing a lot more examples. But let me show you an example for this. This will be example 2 or 1. I forgot. Yeah, 2, right? Not 3. Okay. So example number 2. All right. So evaluate. And part A, let's do the integral from 2 to 2 of 3x dx. Now we know what our answer should be, right? Should be 0. But let me just show you how the fundamental theorem of calculus works. So I know that I could just write 0 and be done with it, but just bear with me. So what I'm going to do is I'm going to integrate 3x. Okay? So I'm going to integrate 3x. So the integral of 3x is 3x squared over 2. Remember I told you guys I'm going to stop doing all the showing of every step, right? Yes, you're supposed to take the 3 out, and then you integrate x, and then x becomes x squared over 2, and then you multiply 3 back in, right? Try to get away from doing every step. Try to learn them a little quicker, because they're also going to take forever. And we're going to go from 2 to 2. Well, according to the fundamental theorem of calculus, my next step is to plug in the top number, which will be 3 times 2 squared over 2, minus plugging in the bottom number, 3 times 2 squared over 2. Well, this will be 6 minus 6, which is 0. So even if you forgot that property, you'll still get the right answer if you do the work properly. Okay? So that makes sense. I could have saved myself a whole bunch of time just by saying, oh, look, A and A, they're the same thing. So that means it's a vertical line. So there's no area. I'm done. Right? But I just wanted to show it to you guys. Now, part B. We're going to integrate from 1 to 3 x squared dx. So what's the integral of x squared? All right, x cubed over what? 3. Okay, I thought I heard someone say 2. So from 1 to 3. So plug in your 3, so it'd be 3 cubed over 3 minus, plug in your 1, so that's 1 cubed over 3. That's 27 over 3. 27 over 3 minus 1 over 3. So this will be 26 over 3. Easy enough, I hope. Hopefully it's not like, oh my gosh, this is too difficult. But it usually doesn't get much harder than that in principle. Of course, I can change up the equations and make them a little bit more complicated, but you're still just going to integrate and then plug in numbers. Okay, so this is called the fundamental theorem of calculus. Okay, now the next theorem here just shows the additive interval property. So we're going to write right here the additive interval property. Let me write it down for you guys. So it says if f is integrable, so is integrable on the interval a to b that includes c, then the integral from a to b of f of x dx is the same as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. I'll draw you a little quick picture. Let's just pretend here's our function. And we'll say this is A, and this is B, and C will be right, let's say, right here. So what this is saying is, notice how A to B is a nice continuous curve. So therefore, it's integrable. Okay? So we know we can integrate it. And then we say we can integrate it from A to B. Okay, great. And we know C is included within A to B based on the definition. So I put C somewhere. So I could integrate all of this. Okay, right now I'm not going to mess with C yet. I'm just pretending I'm integrating A to B. Okay, just integrating A to B. No cuts or anything like that. Just ignore C for now. Here's A to B. What this is saying is, if you want to integrate A to B, but you know that C is found in between there, you could also get your C value and cut it. So notice I'm actually going to go through and draw this in here. I could find that area first, and then find the yellow area. And if I add up both areas, then my answer should come out the same. Okay, so if I were to add the green area and the yellow area, it would be the same as if I integrated everything. This kind of speaks to the first example we talked about, or not even an example, but the little thing where I drew a bunch of geometric shapes. And I said, hey, look, this is a semicircle. This is a rectangle, this is a triangle. So if I just kind of say, let me cut it into small intervals and figure out the area of each one of those intervals and add them up together, it's the same as integrating. This is that property that basically states that. You can cut it up however you want, it doesn't matter. Okay, but you can cut it up however you want. And then if you integrate those intervals and add them up together, you'll be able to get the same answer. So that's called the additive interval property. So let me see. I'm looking at some properties you guys should already know, so we're not going to worry about those. So this is actually the end of section 4.3, what I'm about to do right now. So example number 3. we're going to find the integral here. So evaluate the integral from 1 to 3 of 2x cubed plus 3x squared plus 2x plus 1 dx. So just so you know, this whole lesson you were supposed to do using the left, right, midpoint, and trapezoid methods. This whole lesson. But I just figured you already did that in 4.2. I gave you some problems to try out. You did like 16 problems. So why am I going to make you do this again? Let's introduce the actual integration process instead. That's why 4.4 is called the fundamental theorem of calculus, but we already learned it. We already know how to use it. So 4.4 is the same thing. So like for tomorrow, we will actually go into more detail of like doing some more examples, but you already know everything about the lesson. So that's why tomorrow's lesson should be a lot, less work, I think. So let's see how this one works. All right, so they want us to integrate that big old thing right there. So what I'm going to do is I'm going to start integrating each individual thing. And I'm not going to break it apart because or else I'm going to have 1, 2, 3, 4 different problems. I don't want to do that. Let's just kind of work on this in our head here. What is the integral of 2x to the fourth, 2x cubed? 2x cubed. So 2x to the fourth over 2. Thank you. What's the integral of 3x squared? I don't want it simplified. Just tell me what it should be. 3x cubed over 3. Right now we'll simplify. What's the integral of 2x? All right. And what's the integral of 1? Just x. Okay. Just x. Remember, no plus c's though, right? Notice how I'm not writing plus c's for these because I have definite integration. They gave me my interval, so that's not a question anymore of where I'm integrating. So this should be from 1 to 3. Now let me simplify here. This will be x to the fourth. Whoa, why did I write a 2? I'm sorry. This should be over 4. Sorry about that. 2x to the fourth over 4. So this should be x to the fourth over 2 plus x cubed plus x squared plus x from 1 to 3. So there's my simplification. So what I have to do now is plug in a 3 and then plug in a 1. So let's write this out. So it'll be 3 to the fourth over 2 plus 3 to the third plus 3 squared plus 3 minus 1 half plus 1 plus 1 plus 1. I didn't want to write 1 to the fourth and 1 to the third and 1 squared. Okay, so I simplified immediately. All right, let's see. 3 to the fourth, that would be 9 times 9, so that's 81 over 2 plus 27 plus 9 plus 3 minus half minus 1 minus 1 minus 1, right? If I simplify by just sending stuff over, okay? So right now we'll put everything together. So 81 over 2 minus 1 over 2, that's 80 over 2. So it'd be 40. Now let's add the numbers and then we got to subtract 1, 2, 3. So notice this positive 3 and these are gone. Okay, so the positive 3 and the minus 1, minus 1, minus 1, that's gone. So 27 plus 9, that's going to give me 36. And 40 plus 36, that's 76. So there's my integral value, 76. That's the area found under that curve, 76 units squared. So if you were to graph the function, okay, and and plug in all your information, graph it. That area that it shows you is actually going to be 76. Okay, I'm going to go ahead and stop there, and I'm going to show you guys how to do this on your calculators. Or maybe I can do that on the side here. So let me show you guys how to do this on your calculators. So I guess I could just keep it recording because it'll be good for you guys to see it. So here we go. Let's launch our calculator app. It's going to ask me where my... All right. So check this out, guys. I am going to make it graph something for me, okay? And I don't know how it does it, but let me show you first graphically. All right, so let me type in, I'm going to make something easy so that we're not like spending too much time here graphing this out. Let's do 0.25 x squared. 0.25 x squared, and let's graph it. Okay, so 0.25 x squared, and I'm going to graph it. And this is what it looks like. Okay, now what I'm going to want it to do is I want it to integrate from, let's say 2 to 5. Okay, so I'm going to go, for me it's calculate. I'm going to have to figure out what it is on the Casios. But under the TIs, I don't know if you guys can see it, but right here, you see where the bouncing little cursor is on the graph? So look down, there says calc in blue for me. So I'm going to hit second trace. And then you see how number 7, it says integral of f of x dx? So I'm going to press 7. And then it says, what's my lower limit? So I'm going to press 2. And I'm going to hit enter. Then it says, what's your upper limit? I'm going to put 5. And I'm going to hit enter. And look what it does. It actually colors it in. And it says, oh, you want that area. And it says 9.75. That's one way that you can integrate without actually doing the work. Okay, now I'd want you guys to do the work because on your AP exams eventually it's going to be without calculator. You got to do this by hand. But that's one way you can do it. Now let me show you another way you can do it. I'm going to press second quit so I can get out of here. So second mode. And I'm actually going to have it do an integral. Now, in order to do an integral, you have to go into your catalog. Now, your catalog is found as a blue option under your 0 for most of you guys. Some of you guys, for your TIs, for those of you with the TI 89s, you could actually do an integral symbol in the key. Like, I think it's a diamond function. You can find it there. I can show you later. But let me go second 0, and it gives me a catalog. Now you notice over here there's like a little A value. That means it's alphabetical right now. So that means just press the I for integral. So I would be HI. It's the x squared key. That's your I. And notice how it sends me right to the I's. So I'm going to press the down key until I get to integral. Okay. So integrate. I think that's what it is. INT. Let me just make sure. Yeah, it's the INT one. So right there, INT parenthesis. I'm going to hit enter. Okay. And then it says, what do you want to integrate? I'm going to press 0.25 x squared. That's the function. Comma. With respect to what? Well, with respect to x. And then I'm going to tell it, another comma, correct. From where to where? Well, from 2 to 5. So I'm going to put 2, comma, 5. And then I'm going to close the parenthesis. So that's saying integrate 0.25x squared dx from 2 to 5. When I hit enter, that's going to give me an error. I have no idea why. What did I not do right? Maybe you don't have to put the x. Let me see. Let me check. I know with some of them you do. Let's check without it. No, that's not it. What's the error? 0.25. Oh, I know why. I know why. Hold on. That's not the right command. Give me a second. The command is fnint, function integral, fnint. So second catalog, press F, which is cosine. And you're going to find fn int. There it is, fn int. Sorry, I thought it was integral for you guys, but it's function integral. I'm going to press enter, fn int, okay, fn int. There you go. Now notice I can put a 2 on the bottom, a 5 on top, a 0.25x squared, and then an x where I have respect to. See it? Now when you hit enter, it should give you 9.75. Okay, so I'll stop it right there.